Defenses against disease. Welcome to a captivating exploration of the body's defenses against disease. Our journey will unveil how the human body tirelessly protects us from various threats, much like a well-fortified castle with its own sophisticated defense strategies. Imagine your body as this fortress. The first line of defense, akin to the high walls and moats, is represented by your skin and mucous membranes. These barriers are not just physical blockades but also active protectors, similar to how amylase in saliva breaks down starches into disaccharides, rendering bread sweet over time. These external barriers play a crucial role in shielding us from a multitude of external threats. When a pathogen breaches these initial defenses, the innate immune system, our body's rapid response team, springs into action. White blood cells such as neutrophils and macrophages rush to the infection site, engulfing and destroying invaders in a process reminiscent of how symbiotic microorganisms in a shipworm digest cellulose from wood. Accompanying this response is inflammation, causing redness and swelling, signals of the body fighting back. Fever, another response, creates an inhospitable environment for pathogens, akin to how external heat changes protein structures. Deeper within the fortress lies the adaptive immune system, a specialized, highly trained unit. This system includes organs like the thymus and spleen, lymph nodes, and cells like B cells and T cells. These components work together to target specific threats, much like a security system that differentiates family members from strangers. This discernment is crucial, just as it is essential for shipworms to have symbiotic microorganisms to digest wood. The adaptive immune system strategies include humoral immunity, involving B cells and antibodies, and cell-mediated immunity, where T cells destroy infected cells. Helper T cells orchestrate this response, directing other cells into action. This precise system, capable of distinguishing self from non-self, ensures targeted and effective defense. Acquired immunity further strengthens our defenses, developing through exposure to pathogens or vaccines. It's akin to building a repository of information on past battles, prepping the body for quicker and more effective responses upon re-encounter with the same pathogen. Beyond our natural defenses, antibiotics and vaccines provide additional support. Antibiotics assist in battling bacterial infections, while vaccines prepare the immune system to fight specific pathogens without causing the disease. Yet, our immune system is not without its flaws. Allergies arise when it overreacts to harmless substances. Autoimmune diseases occur when it mistakenly targets the body's own cells. Immune deficiency diseases, like AIDS, arise when parts of the immune system are missing or dysfunctional. The immune system's role extends to combating cancer, often recognizing and destroying cancerous cells. Treatments like immunotherapy leverage this ability, enhancing the immune system's capacity to fight cancer. Our understanding of the immune system even informs us about the effects of substances like caffeine. Contrary to increasing certain hormones, caffeine actually decreases the amount of antidiuretic hormone, ADH, in the blood, leading to increased urination and potential dehydration. Chemical control of the endocrine system. In the intricate dance of the human body, the endocrine system's role is both subtle and profound, orchestrating a complex series of events that regulate everything from growth to metabolism to mood. It is through this system that the body communicates within itself, using chemicals that command a presence as soon as they enter the bloodstream. The journey of an endocrine hormone is a fascinating tale. It starts with its synthesis in an endocrine gland. Take, for instance, the thyroid hormone. Produced in the thyroid gland located in the neck, this hormone enters the bloodstream and travels to target cells throughout the body. It binds to receptors with a specificity that ensures the right message gets to the right destination, akin to sending a coded message that only the intended recipient can decipher. Upon reaching its target cell, the hormone's message is translated into action. If the hormone is a peptide, such as insulin, it latches onto the cell's membrane, triggering a cascade of events that culminate in the cell absorbing glucose from the blood. This action illustrates the precision of hormonal communication, highlighting the hormone's pivotal role in maintaining blood sugar levels, an essential factor for energy regulation. The body's hormone release is controlled with precision. It's a system of checks and balances, where the effects of hormones are monitored and their levels adjusted to maintain homeostasis. For example, when blood sugar levels rise, the pancreas secretes insulin. This hormone then lowers blood sugar by facilitating its uptake into cells, and once the levels are back to normal, insulin secretion decreases. This feedback mechanism ensures that the body's internal environment remains stable. The mammalian endocrine system is a network of glands that include the pituitary, thyroid, adrenals, and pancreas. Each of these glands releases specific hormones that have distinct effects on the body. The pituitary gland, often called the master gland, regulates the function of other endocrine glands. The thyroid controls metabolism, the adrenals respond to stress, and the pancreas regulates blood sugar. When it comes to defense, the body has a specialized set of cells that operate like a highly trained military unit. Among these are the cytotoxic T cells, which directly attack and destroy infected cells, ensuring that viral infections are contained and eradicated. Their precision in identifying and eliminating infected cells is a testament to the body's sophisticated defense mechanisms. In contrast, when the body encounters a pathogen for the first time, like a bee sting, it creates memory cells. These cells remember the pathogen, ensuring that if the body encounters the same threat again, the response is faster and more intense. The creation of these memory cells underlines the importance of the immune system's ability to learn from past encounters and respond more effectively to future threats. Interestingly, the immune system's memory is so crucial that if a virus were to prevent the creation of these memory cells, it would be targeting the lymphocytes, particularly B cells. These cells are the body's historical record keepers, and without them, the body would struggle to mount an effective response to previously encountered pathogens. When considering the role of medication like aspirin in the management of fever, it's worth noting that while aspirin can reduce discomfort, it may also diminish the activity of the body's defense cells, like phagocytes, which are more active at higher temperatures. Thus, while aspirin can alleviate symptoms, it may also potentially lower the efficiency of the immune response. Lastly, the history of human disease offers a stark reminder of the immune system's limitations and strengths. The devastating impact of Old World diseases on Native American populations exemplifies this. Without prior exposure to these pathogens, Native Americans lacked the necessary immune memory to fight off these diseases, a direct contrast to Europeans who had, over centuries, developed some level of collective immunity. The body's ability to defend itself, remember past infections, and maintain internal balance through the endocrine system's chemical messages is nothing short of miraculous. It's a system that has evolved over millennia to keep us alive and well, a testament to the resilience and adaptability of life.